Hello everyone, my name is Tino from Digitex Systems, and today we're going to have a quick view and quick tour of our comprehensive data analysis package called Observer. Once we start the Observer data analysis toolkit, a simple menu like any other software for seismic analysis showing us what we can do here. The first thing would be, of course, to open up previously recorded data. For the purpose of this demonstration, we're going to open a record containing the record from the El Centro earthquake. So we're going to go to the main menu and I'm going to press on New Signal Graph, and I'm going to select my ASCII file containing the data from that record. Of course, the application, because it's a multi-purpose application, detected that there is no metadata, meaning that we do not have calibration and sensitivity information and of course the sampling rate for this data. So I'm going to have to select that manually. In this case, I know that El Centro earthquake was recorded with 50 samples per second. So once I select this, I can go to OK, and then my application will load this record. Now we see one chart showing us the data from this record and the duration of the data, which is actually around 30 seconds. What we have here, from analysis point of view, we have many different tools for analysis, which are basically a standard when we do a seismological analysis of acceleration data. For that purpose, we can go to the analysis tab and see what we have available. The first one is the one that we actually see now, which is called the signal graph. First thing that we need to do, as any other person who analyzes the seismological data, is to start with the pre-processing of the data. That means that we need either to apply the trending to the signal, or to remove the mean, or to apply some kind of a decimation, or to apply some different filtering method. All those analysis tools are available on this right panel, where we can see that the trending, for example, we have several options here. We have a simple mean removal, or we have a linear trending removal, or we even have a polynomial remove of the trend. Decimation is, of course, the factor at which we decimate the data in case we have a record which was sampled and recorded with a high sampling rate. And we for sure know that by decimating we will not disrupt the main signal. Filtering method is offering a standard type of filters used for signal processing, like Butterworth type of filter, Chebyshev 1 and 2 types of filter, Bessel and elliptic type of filter. Filter types are based on the standard libraries. Again, like we can use low pass, high pass, and band pass type of filtering. Then we can select the filter order, and we can select the cutoff frequencies for the lower and the higher range. So once we load the signal, we can do standard pre-processing algorithms for working with acceleration data. For example, we can do the trending of the signal by simple mean removal, or even apply a polynomial type of the trending. Then we can do decimation, or we can do a simple filtering of the data. So for this example, I will just apply simple mean removal of the signal, and I will apply Butterworth bandpass filter that will filter my data in the ranges from 0.15 up to 10 Hertz. Please consider the Nyquist frequencies when you apply low and high cutoff frequencies when doing filtering. Besides this, we have additional types of analysis. So we can do integration of the data. So if I simply press the button integrate, then the application will automatically integrate and calculate the displacement as well as velocity values from these acceleration signals and showing them on a separate graphs. Additional type of analysis and additional setting is that regarding we can do a fast Fourier transformation of the signal by simple pressing on the frequency button. So it will show us a nice fast Fourier transformation window, which will actually show us the peaks of the frequencies that were consistent within this signal. Regarding the FFT, we have several windows that can be selected as an options, including Hanning, Hamming, Blackman, and Bartlett type of window. And besides the standard FFT, we can do a power spectral density estimation of this data by calculating a different frequency domain method. All of these frequencies can be modified to show different ranges of the frequency, in order for us to focus on the exact frequency range that we are interested. Going forward, then we can just do a response spectra of the signal, which is actually application that functionality that will calculate the shock response spectrum and actually the distribution of the energy of this signal over the frequency period. So this is a very good analysis tool that is showing how much energy was distributed over which frequency within our signal. Additional functionalities that we can do here is the autocorrelation, which is actually autocorrelation between each of the channels and cross-correlation between different channels of this signal. So for example, my default is to cross-correlation to be done between channels number 1 and 1, but I'm going to do a cross-correlation now between channels 1 and channels 2. So the method will be shown. The response spectrum settings, which we previously saw, also have some configuration parameters in terms of using the appropriate method for calculating the response spectra and entering different damping values for which we would like to calculate this response spectra. Standard damping ratios are 2 and 5%, and we can use them to calculate and to see various responses of our system using this input, in this case, earthquake force. In general, this observer application and the functionality of this application are divided into this part that I already explained, and additional part is related to advanced analysis using operational model analysis tools. So for that purpose, I'm going to use a different data set with a predefined geometry of both building and bridge, so you can see how this application actually works. The Observer Data Analysis Suite is a comprehensive toolkit which can be used for different types of seismic analysis on already recorded acceleration data. Among the standard types of analysis, like calculating the displacement, the velocity values, FFT spectrum, response spectrum, and so on, Observer Data Analysis Suite is consisting of a powerful model analysis tool. In order to showcase and demonstrate how this actually works, I'm going to open a predefined method, a predefined data, which is actually a model analysis of a building. So once I select my file, the data will be loaded immediately, and the application automatically will let me know that there is a available setup prepared for OMA analysis. I'm going to do that later. The first moment would like to show you the data and how we should operate the data during this process. For example, I have loaded many number of channels here on this setup, and by simply clicking on this button, switch view, and previous selecting, let's say, 20 number of channels, I can tell the application that I would like to see 20 channels at a time on a separate graph. This way, using the standard analysis tools for the trending, for decimation, and for filtering, we can analyze the data and start preparations for the model analysis. The preparation for model analysis includes preparing a geometry setup for that specific building in this case, and assigning each channel from each sensor to that specific point along with their data of recorded data containing the acceleration. So once we already have a prepared setup and project for this operational model analysis, I'm going to simply go to the tab called Model, and I'm going to do Initialize of the model analysis. What this will do, this will load the previously calculated and previously created model of the building. So here we can see that we have a very nice model of a building with many sensor locations. We have several floors that are actually equipped with different types of accelerometers, and they are all oriented in different locations. The model analysis toolkit that is contained in the Observer contains several methods for model analysis, among which are the methods from the frequency domain decomposition group, consisting of standard FDD. Then we have an enhanced FDD called EFDD, and frequency spatial domain decomposition method. Additionally to those three frequencies, we have two of the methods from the stochastic subspace identification group, called SSI data-driven and SSI covariance method. At the end, we also have additional method for modal analysis called polyreference least square frequency method, and all of those are available with the basic purchase, with the basic license of the observer. Here, within this setup, it's important to know that we have only one setup loaded. Later, I'm going to show a different example of a multi-setup OMA analysis model. So this sample here, I have previously loaded my data, and I can see that I have total of 29 channels of acceleration recorded within this data. Before we start with an analysis, we need to decide and set up several parameters regarding the model analysis, like which of the frequency groups we would like to enable. For the sake of this demonstration, I have enabled the FTD and the SSI group, and then we need to do some parameters related to the basic pre-processing of data. So I told my application, I set this configuration and tell the module that I would like to do the trending, I would like to do a decimation with a factor of 8, I would like to filter the data with a basic Butterworth bandpass filter with the frequency low and high from 0.15 up to 20 Hz. Additionally, I'm setting up different parameters related to the modal analysis itself, like the block rows for the stochastic subspace identification and the additional parameters that are used during generating on the singular value decomposition diagrams. Once I'm ready with this configuration and I'm satisfied with all the parameters that I have done, I'm gonna just go and click simply the Apply Changes button, which is actually initializing the operational modal analysis engine. What is gonna happen now is that we need to wait a little bit more while this analysis is finished, which already is done, and we need to go to the actual, to continue with the actual modal analysis procedure. For that purpose, I'm going to click the Analysis button, and that will show me the results from my initial operational model analysis. What does that mean is that combination of frequency domain decomposition methods and the stochastic subspace identification methods, I have several diagrams. The first ones are called singular value decomposition, and using the SSI type of methods, we are receiving so-called stabilization diagrams. So from this combo box here, I can select any of the methods that I previously explained. So for this example, I'm just gonna select the EFDD method, which means that we're gonna use the enhanced frequency domain decomposition in order to do a modal analysis of the data for this structure. Once we have selected an appropriate method for modal analysis, which in this case I have selected the EFDD method, and by observing the SVD diagram, after pressing on the Calculate button, we receive the actual modal analysis from the toolkit, meaning that we have an animation of the building on that frequency, and we have several additional graphs, like a Bell function, like autocorrelation function, portion for fit or fit and frequency, and damping correlation. The purpose of all these additional diagrams is to help us clearly identify and determine that this is actually a natural and correct natural frequency. What we are seeing in the bottom right corner here is that we see the selected frequencies, the values that we have picked from the graph, but also we are seeing the calculated frequencies and also calculated damping ratios. So by simply pressing the frequencies, we can see the different graphs from each one of them, and this should be enough as of this moment for us to determine that we have correctly identified several natural frequencies. What should we do next is that we should not stop here using just one simple method, but we can use several different methods with one simple goal to confirm that identified frequencies are really the ones we need. For that purpose, I can just select, for example, basic frequency domain decomposition method, which I'm gonna use, and I have selected different 3 frequencies in this case. This is no problem at all because the program can calculate any frequencies that we picked from the SVD diagram. Now, if we press on the calculate, we're gonna see the calculation on of the software, and as a result, we'll see the animation of the different frequencies and how our building is moving on a micro level on selected frequencies. It's important to know that the FDD method is the only one that actually does not calculate the damping ratios, hence the not available values here that we see in the table. Continuing with the analysis, I can decide that I can use another additional method from the stochastic suspects identification group called SSI data-driven method. And instead of singular value decomposition, we have the stabilization diagrams, which are actually showing us the identified stable and identified unstable poles. So by using the peak-picking method, I'm identifying several frequencies, which appears to be basically more or less the same that we already previously saw. And again, I'm gonna do the calculate button here with the simple goal to calculate now the natural agent values for this building for those selected frequencies. Again, I received the calculated frequency and damping for each frequency, and I have received the appropriate damping ratios for each frequency. This is a very highly interactive application, which is allowing me to change the view of the graphs in any way. So for me, it's very important that I would like to see to have the animation on a much bigger screen, or I can just simply move it to anywhere on the top where I would like them to be. So after observing and after working with the data and observing all the additional and diagrams that are being generated, it is time for us to go to the final step of the operational model analysis, and that is to confirm the identified frequencies and natural frequencies and damping ratios from each method using the model assurance criteria. That will be our final step in identifying and determining that the actual identified frequencies are the real ones. So I'm just gonna go to my model and I'm gonna press on the verification button. So what will happen now is that I will see a simple animation from selected 2, and on the upper left corner, I can see that during my analysis, I have used 3 types of methods: EFDD, FDD, and SSI data-driven method. So what I'm gonna do is I'm gonna click one frequency from the FFD, and for example, I'm gonna click the same frequency from the different method. Lower left corner is actually showing us the MAC matrix, which are actually showing the red pylons, showing the number of 1, meaning that those exact frequencies are present in both calculation methods. So for me, that's a good sign that I have very good and correctly identified the natural frequencies. So I'm going to do the same thing with the other frequencies from the other method, and I'm going to confirm that. Even I can do a comparison between the SSI type of method and the enhanced frequency domain type of method, with all simple goal to have a value of the model assurance criteria as bigger as possible. In other words, as close to 0. So here we have a calculation of almost 0.4, which means that again, both methods have identified the frequencies in a correct way. I can confirm that additionally by observing the animation, and I can see that my building actually is animating on those frequencies very good. While doing the operational model analysis, the Observer Data Analysis Suite is also offering some additional tools that will help us doing model analysis, again with one simple purpose, that we identify clearly and correctly the natural frequencies and damping ratios. Those tools are something like autocorrelation, that we can select, we can see the autocorrelation of each channel, the power spectral density of each channel, the probability matrix of each channel, and the normal probability plot for this channel. Additionally, the Observer Data Analysis Suite is accepting and is able to calculate and to do operational model analysis using a multi-setup project, meaning that with just a couple of sensors, for example, if we have 5 accelerometers, we can do operational model analysis and measurement of a building with, let's say, 100 measurement points. That means that we can do at least 20 different measurements, and by using a reference type of channel, we can have one picture from the building, and we have a situation in this case like we would have been using 100 accelerometers at the same time. This is very useful practice, and doing model analysis and measurement of huge structures when we have a limited number of accelerometers. For that purpose, I'm going to load an additional bridge project, and we're gonna see that we have a recording here for using multi-setup process. Again, the observer, the application has identified that I have already created geometry file and a project file for this measurement. So it's asking me, would I like to begin the OMA initialization process now? Of course, I'll go to yes. And again, I'm gonna select some different method types. So for this example, again, I'm gonna select the FDD and SSI groups of methods, and we can see the geometry of the method that is actually with many points on both sides of the bridge. Here on this window, we can see that actually this project is containing 10 setups, which means that we had a situation when we have used 5 triaxial accelerometers dispersed on over 10 different measurement setups. All of these are taken into account using the module, the background module that is actually doing this analysis is taking all this into consideration. And like the previous time, once we select the appropriate pre-processing characteristics and decided which type of filter, the decimation type used, and all the parameters needed to the OMA analysis, we can just click on the apply changes, and the system will start calculating the initial process of the model analysis, which is again calculation of SVD, singular value decomposition, and stabilization diagrams. So once that is finished, the application will be back to this screen, and we need to continue by pressing the analysis button. Here we have somewhat different type of SVD diagrams and stabilization from the building. So again, we're going to start with the same process, for example, by selecting the enhanced frequency domain decomposition method. Here, the SVD diagram is showing us many different peaks, which I would like all of them to be checked and see which one of them is a real natural mode containing both natural frequencies and damping ratios. So once by using the peak picking method, I have selected those frequencies. We can see them here on the graph. I can go and press the calculate button, which is actually gonna do the final step of my model analysis. So we have seen a nice first mode of 1.26 Hertz and the first natural form of moving of this bridge. Then pressing on the second one, we can see the little bit torsional mode and the third mode with appropriate damping ratios and so on and so on. So total of 6 modes have been identified here, all with different shapes and all with different frequencies and damping ratios. Again, I'm going to use a different method. I'm going to use the SSI covariance method in this case, and I'm going to select 4 frequencies that have been identified from this stabilization diagram. Again, by pressing the calculate button, I can just calculate and finally compute the natural modes for this bridge. So again, I'm seeing the frequencies, I'm seeing the damping ratios for each of these frequencies. Again, like with the previous step, we need to do a verification by using the model assurance criteria and by simply selecting the similar frequencies for both methods. We can do a comparison and make a final determination of the validity of those modes. For the end, I would just say that this is a very comprehensive, a very handy and very user-friendly tool that can be used for many different kinds of analysis, including the operational model analysis. And I'm just going to show that even though we did a lot of calculation, a lot of processing here and analysis of the data, we can sum up all of that into a simple report. So there is a button and there is a simple functionality here which says generate the report, which will actually take all the analysis that I have been doing using this application for the last hour or two, and then it's going to create a simple PDF report containing all the graphs, all the images, all the animations, all the calculated data from this application. So once I start on generate, we can just wait for this to be generated. So my report has been generated. So I have two types of reports here. The first type of report was from the modal analysis of the building that I have been doing. So once we open this PDF report, we can see that we have a very nicely structured report, PDF report containing data for all channels with a lot of information like sampling rates, scale, offsets, everything that was contained in the input signal. Then we have some calculations regarding calculation of the minimum, maximum, average, standard deviations, RMS, many tools and many analysis and many data are being calculated of this report, containing all the graphs, containing real-time acceleration values, real-time acceleration charts, then corrected acceleration diagrams if we did some detraining, then containing the frequency spectrums and all that, with ending with a calculation of the modal analysis along with the print screens of all my animations together and appropriate animations for each identified frequency. So let's see the generated report for my bridge, same as the previous one. Many data, many applications, many different methods used with many different graphs and tables with many numerical analysis and signal processing tools. So like we are seeing on the picture. And so we can go scroll down to see the actual model analysis part where the identified model shapes and identified frequencies together with the damping ratios and animations, of course, are being contained within this report.